So right now we have two competitors, volume, design 1, design 2. From 1 to 2, we arrived on the path called scooping out the material, hollowing. We're drilling the inside of the rod, drilling it out. The other technique would be to still have it solid, but to taper it. And that would be design number 3 that I skip, because by the time you deal with, as you'll see, 4 of them, you kind of run out of curiosity. In design number 3, the volume, meaning the result of tapering a solid rod, like the tree branch, that is a tapered round beam, okay? V3 turns out to be 4, and then that unit called EP delta over SMA squared. Also very impressive. Now you reduced 12 to 4, meaning instead of multiplying by 1/2, you multiply by 1/3.
Does it taper down to a point?
No, it doesn't. By the way, we'll see that very shortly. It doesn't, and that's something else with hitting people over the head. Tapering does not mean necessarily this way. You discover, so that's no. Tapering is to a profile that looks like a dull knife. Okay? Every single tooth, no matter how big or small, or how complicated its top surface that does the cutting, is in fact a dull knife, because otherwise the sharp crest will be breaking off. Get it? I'll make a sketch to remind me to ask you a question at the end, but not now. Okay, so that would be one direction in which to explore, and in either of these two directions, you have exploited 1 degree of freedom. 1 degree of freedom was only 1 because there was a relationship between L2 and L2, and everything was fixed and going from one drawing to the other. This is one way to change. Another way to change, maybe you do even better if you change 2 ways at the same time. Meaning, this way, design number 4 would be one showing both hollowing and tapering. And that drawing, which takes a little more time to analyze, is this. I don't know whether you are familiar with the original design of the big pen. The top of the big pen, the one that was originally blue, looked like this. Also, this is the shape of the thick end of the quill, the biggest feather on the long distance flying bird. The end that's implanted in the wing. And so this thing has a length L4, and obviously the loading P and the deflection delta, all these things are old news. And right here, an annular cross section that depends on location X. A cross section where this thickness T of X is a small fraction of the radius at that location. So this is the radius. Then that's the relationship that we adopt, as we did in the case of design number 2. And now comes the answer to the question of why is this shape rounded at the tip, or why it should be rounded at the tip. Obviously, it should be rounded at the tip so it doesn't break. Every sharp feature in a loaded structure, you've heard the word stress concentration, those have to be avoided. Protuberances that are sharp will be the first to break, but also negative protuberances, meaning indentations that are sharp, those are basically invitations to cracking. And all right, so those are stress concentrators to be avoided. And we avoid the stress concentration in this design because we have freedom to imagine and say, look people, we have reached the end of the road of eliminating the material that's not stressed to the maximum allowable level. Therefore, let's declare that the entire dorsal fiber, all of it to the tip, is inhabited by material stressed to the maximum allowable level. And the same is true about, by assumption, about the ventral fiber. So that's what we say, okay? And then we have this formula from the template called the first formula, Roman 1, which once again was written as the stress in the solid body is equal to the bending moment divided by the area moment of inertia times y. And now we say, look, everywhere, this is SMA at all x and y. And then we figure out the bending moment is the force times the arm. Here now you see the origin of the expression bending moment. Again, moment is not about the seconds that are ticking on the dial of the clock. Moment means movement, and that is what what happens when you crank something with a force here and then rotating it with this arm, with the arm of length x. So the word moment, which is the product of force and then displacement, comes from the imagination of something that turns because you apply force. Get it? All right, so px here. And then downstairs is the area moment of inertia of the annular cross-section, which I erased the formula, is this, let's call it I, okay, right now we're in design number 4. I4, it is a number that's of units, meter, forget about meter. It's proportional to this diameter or radius. Let's put radius to power 4. So now we're no longer writing equal sign, but order of magnitude. And then this y, of course, is the radius. Get it? So that's what we get if we substitute the innards on the right-hand side. Meaning that on the right-hand side, we have a product of x. In other words, I'll say that the right-hand side there is as x, over radius to power 3. And that group, according to my thinking, must be constant. Because SMA, in my imagination, is the same throughout the upper fiber and lower fiber. All right, and that gives me the answer for you. What is the shape of the beam, this beam in profile? This hollow tapered tube in profile. It is a shape where R varies as x to 1/3, meaning this shape. If this is R, and x changes from 0 to any x, then the curve discovered here has this shape. A round nose. Round nose. It's very important to keep this in mind, to learn now if you did not learn this on your own much earlier. If the curve is x to power n, then this is a curve for n less than 1. As it is the case here, n equals 1/3. Important to know, because this curve is not to be confused with the straight line that emanates from the origin. The straight line would be n equals 1. And then to beat this demonstration to death, what would be the shape of the curve if n is greater than 1? Well, that will look like a parabola, meaning this way. To exaggerate, but that would be n greater than 1. Okay, so that's not what we have. We have not that and not that. We have this one. And to are listed like parroting the previous formulas. This time they're listed as equations 10, 12 through 10, 14 in the book. And then the result, meaning after you go through this somewhat more complicated analysis, you find that the volume, which today I call it V4, it's called V3 in the book. Anyway, V4 turns out to be only 2 of these volume units. Amazing, huh? So let's take a look in let's go retrospective. If the performance here is 2 volume units, it was 6 volume units here. It was here 4 volume units. And of course, 12 here. We discover several things that happen more than once on this very drawing. Hollowing is a powerful method because it reduces the expenditure to half, meaning it multiplies the expenditure by 1/2. See, that's hollowing. Tapering is similar but even better. It multiplies the expenditure by 1/3. That's tapering. And because tapering multiplies the expenditure by 1/3, then obviously going from this design with 6 to this design, the 6 was multiplied by 1/3. You see? So that's getting from 1 to 2 to 4 by first hollowing and then tapering. But you may have gone the other way to arrive at 4, first by tapering and then by hollowing. And what do you know about hollowing? It reduces the expenditure by a factor of 1/2. And that's why you arrive from 4 units to 2 units. When you do these problems that have to do with the change in performance, because you make one kind of change, it will grow on you, meaning because you have memory, the realization that one kind of change produces one kind of change in performance. So change in architecture corresponds to change in performance. And if you have a feel for that, then, meaning knowing what happens when you employ only one method, and then only one method, well, what happens when you imply both is the product of the two, meaning this one. Said another way, Adrian did not have to do the analysis that I suggested here to find the value of V4. I could have guessed it through this technique of shooting in the dark, you see. So that's the power of theory. It's like you're shooting in the dark, but you know what is in the dark. You know where to shoot.